So we're doing the probability unit in Math 30-2, and today we're going to look at topic 4A, independent and dependent events using the product rule. So just to point that out to you, product rule. So if we think of product, we think multiply. So you can bet we're going to be multiplying today. All right. The goal is to understand and solve problems that involve independent and dependent events. Now, this is different than mutually exclusive and non-mutually exclusive events. So let's explore. Here is the exploration. Are both girls in this example, Layla and Karis again, equally likely to draw 2 red marbles? So, Layla and Karis each have 19 marbles, 11 red and 8 blue. So they each have 19 marbles, 11 red, and 8 blue. So we can see what they have. Layla puts 7 marbles and 3 blue in bag 1, and she puts the rest of her marbles in bag 2. So she splits them up in 2 groups. Karis places all of her marbles in bag 3. Layla then draws 1 marble from bag 1 and 1 marble from bag 2. Karis draws 2 marbles from bag 3 without replacing them in between. So we're going to kind of walk through this. Let A represent Layla drawing a red marble from bag 2. Let B represent Layla drawing a red marble from bag 2. And are A and B independent or dependent events? Explain. We would say that these are, well, let's look at what independent and dependent events are. Independent events says the outcome of the first event does not affect the outcome of the second event. And dependent events, the outcome of the first event does affect the outcome of the second event. And when we say the outcome, we're talking about the probability. So because Layla has her marbles in 2 separate bags, drawing 1 out of one bag and 1 out of the second bag, we would say these are independent. They're not going to impact that. So we're going to figure out probability A. In bag A, she has in total 10 marbles. 7 are red and 3 are blue. So probability of A will be 7 out of 10. In bag 2, she has 9 marbles. 4 are red and 5 are blue. So determining probability of B is 4/9. Now, the probability that both events A and B occurs is 28/90. And how do we get that? We get that by multiplying. And we can write that as either as P A and B or P A and B. That's remembering our set theory nomenclature as well. Now, how do we get that probability? Well, we take our 7/10, we times it by our 4/9, we get 28/90. We multiply them. Okay? Now, looking at Karis' situation, Karis draws a red marble from bag 3 and on her first draw and keeps that marble out. So that's C. D, she draws a red marble from bag 3 on her second draw. Are these independent or dependent events? Explain. Well, dependent events say that the outcome of the first event does affect the outcome of the second event. In this case, because after Karis draws that first one out, she's changed the total number of marbles in her bag. She has changed the probability of the second event. So this would be dependent. Okay, and this works a little different. So let's figure it out. Oops. So determine probability of C. Well, in her bag, she's got 19 marbles and 11 of them are red. So that's probability of C. Now we're going to determine the probability of event D. Now, because she's taken a marble out, she no longer has 19 marbles in her bag. Now she has 18 marbles in a bag. And if she took the first marble out and it was, in fact, a red marble, then that means she only has 10 marbles remaining in there. So probability of event D happening is 10 out of 18. Now that depends on whether she pulled out a red marble. Okay? So it is dependent on that first action. Okay? Now the probability that both events, C and D, occur is 110 over 352. And again, we can represent them. They can write it as P, C, and D, or like so using our set notation. Now, can we get that probability? Well, if we take PC times PD, so 11 over 19 times 10 over 18, we get 110 over 342. So again, we multiply each of them. Okay? Now, how can we explain tell if two events are independent or independent? The first thing is, or the way we do is we ask the question, does the first outcome affect the second? So it's really, does it have an impact on the probability of the second? Okay? And you have to think them through when we're doing them. Let's look at some information here. Let's summarize. Independent events are two events in which the outcome of the first event does not affect the second event. Okay? So using the product rule for independent events, the probability that two independent events will both occur is the product of their individual probabilities. Okay? So that is the product rule. Products mean multiplying. Dependent events are two events in which the outcome of the first does affect the outcome of the second event. Again, we can use the product rule. We just have to make sure that we've taken into consideration the impact of that first event on the probability of the second event. So we multiply, and it's P and B is equal to P of A times P of B and A. Okay, so this means the probability of B slash A is the probability that the second event B will occur given that the first event has already occurred. Okay, so B is reliant on A already having occurred. So we're going to go through, we're going to look at some different situations, and we're going to decide whether they are independent or dependent events. So, example, independent versus dependent. So we're going to classify these as either independent or dependent. Rolling a 4 on the die and tossing heads on the coin. So does rolling a 4 on a die affect what we're going to toss on the coin? No, it does not. So these would be independent. Okay. Rolling a 2 on a die and rolling a 5 on a different die. Well, that should not impact anything. In fact, even if you rolled a 2 on one die and re-rolled that die, it would still be independent because you have the same chance regardless to roll the next one. Okay? Rolling a 2 the first time on a die and rolling a 5 the second time on the same die. I've answered that question. Again, it's independent. It's not going to change the probability of that happening. Okay? Drawing a heart from a deck of cards, then drawing another heart from the same deck of cards without replacement. Okay, that is a key point here. Without replacement. So because we don't put the card back, we now no longer have 52 cards. So sometimes replacing or not is going to affect whether the two events are independent or dependent. Because we didn't replace the card, we now have 51 cards and we have one less heart. So it will change the probability, and now we have a dependent situation. Drawing a black card from a deck of cards, then drawing a red card from the same deck with replacement. Because we put this card back in, we still have 52 cards, and we haven't changed the proportion of black to red. So this would be independent. Okay. Picking a blue marble from one bag, then picking a purple marble from the same bag with replacement. Key point. We put that marble back in, so we have not changed what's in the bag. It will be independent. Okay. Picking a blue marble from one bag, then picking a purple marble from a different bag without replacement. Okay, well, we haven't replaced, but it's a different bag. Okay, so it's like the first example with Layla and Karis. The bags haven't changed, so picking that first marble is not going to impact the second pull. So it would be independent. And I need to learn to spell. Independent. Okay? Hopefully, those examples are helping you understand the concept better. Now, example number 2. Determining probabilities of independent events. So, Mokhtar and Chantel are playing a game that involves rolling a dice and tossing a coin. Find the sample space for one die toss and one coin toss by drawing a tree diagram. So, we roll our die. We could get a 1, 2, 3, 4, 5, or 6. And then we do our coin toss, so we could get heads or tails, heads or tails, heads, tails, heads, tails, heads, tails, heads, tails. Total outcomes, 12. Total outcomes. Okay, so we could roll a 1 and get a head, roll a 1, get a T, a tails, 2 heads, 2 tails, etc. So now we have our tree diagram, and it is going to help us guide us through the next questions. So find the total number of outcomes in the sample space. We have 12 outcomes that are all different. Use the sample space from the tree diagram to find the probability of rolling a 6 and getting heads. So let's see what that looks like. So we roll a 6. I really want the highlighter, not the marker. And then we get the heads. Okay, so there is only one option that fulfills that requirement. So the P of 6 and heads equals 1/12. Label each branch in the tree diagram with its probability. Use this new information and the product rule to find P, 6, and heads. Well, looking at this, the probability of rolling a 6 is 1 out of 6, right? Okay, and then the probability of getting a heads is 1 out of 2. Okay, so if we use that, probability of 6 and heads is equal to probability of 6 times probability of heads. So that would be 1/6 times 1/2, which is equal to 1/12. So we get the same amount. So it doesn't really matter which way you get there, as long as you get there, right? Okay, so let's keep going with more examples. Example 3, determining probabilities of independent events. So the probability that a student completes a math assignment is 0.8. The probability that the student completes an English assignment is 0.3. Obviously likes math better because that's 80% and only 30% with the English. Assuming that these events are independent, find the following probabilities. So the probability that they complete both assignments. So the probability that they do math and English. So we take our probability of math times our probability of English. So that would be 0.8 times 0.3, which is 0.24. So the probability that they do both, 0.24. The word, or that the student completes neither assignment. Now the word neither means that the complement of the first event and the complement of the second event. So if we're to write those out, it's the probability of math prime and English prime. So we have to think about what would they be. They would have to be what we would add up to get 1, right? So math prime times English prime. Now, if we're looking at that, it's 0.2 because 1 minus 0.8 equals 0.2. And then 1 minus 0.3 is 0.7. So that's how we figure out those the prime probabilities. So this would be 0.2 times 0.7, which is equal to 0.14. So the probability that the student does not complete either assignment is 0.14, which is 14%. Okay. Right. Okay. So let's continue. Example number 4, comparing probabilities of independent and dependent events. So we're just going to compare. One situation is going to be independent and one will be dependent. If we have events here and we have replacement, it's going to be independent, right? If we don't replace, it will be dependent. So let's see how that impacts what our probability is. So 2 cards are drawn from a standard deck. Compare the differences in how replacing the card after the first draw versus not replacing the card affects the probabilities of the events in the table. Calculate the probabilities using a formula. So the probability that both cards are clubs. So probability clubs times probability clubs. There are 13 clubs in each deck of 52. Because we're putting it back in, both probabilities are 13 out of 52. We will get these reduced to 1/4 times 1/4, so it equals 1/16. Okay? Now, the next situation is if we don't replace the card. So it's probability of clubs times probability of clubs if club happened already. So that's what that straight line club means. So the first one is 13 out of 52 times, now we only have 12 cards that are clubs and we only have 51 cards. So when we multiply that through, we're going to get 1/4 times 51 divided by 12. So this reduces, I believe, to 4/17, which will give me 1/17. So slightly different. If we translate both of those into decimal, this will be 0.0625. And this one will be 0.05882. That's enough decimals. Okay? So let's see what happens with the rest of the examples. A red jack first, and then a black card second. So for this one, we're going to have probability of a red jack, and then probability of a black card. Now we're putting them back in each time. So there are 2 red jacks, 2 out of 52, and there are 26 out of 52 black cards. So 2 out of 52 reduces to 1/26, and 26 out of 52 reduces to 1/2, So that equals 1 out of 52. Or if I put it in decimal form, 1 divided by 52 is 0.01923. That's enough decimals. Usually I'll specify decimals, but just it's easier to compare decimals and fractions because we don't know if we're going to have the same denominator. For the next one, probability of a red jack times probability of a black card if a red jack was pulled first. And when we're not replacing and we're doing a dependent situation, we need to establish what happened first. So, probability of a red jack we know is 2 out of 52. Now, probability of a black card, we still have all 26 black cards, but now we only have 51 cards. Okay, so when we reduce this, if you reduce your fractions dividing things out, you're going to get 1 out of 51, because we're going to divide out 2 times 26 is 52, so the 52 divides out of the top and the bottom. So this will be 0.01960. Okay, so it's an interesting if you look at both of them. Because you can't just assume that dependent events will have a lower probability. In the first situation, yes, pulling 2 clubs, it did have a lower probability when it was dependent. But in the second situation, it actually has a higher probability because by pulling a red jack, we've actually increased the odds that you will pull a black card for your second choice. So it's good to do the work to kind of make sure you know what's going on. Let's check here a red jack and then a black card. A red jack and a black card. So here, the important thing is that in the first situation we said a red jack first and then a black card second. Here we're going to kind of look at our order. Okay, so we know what happens in the situation ahead, but we just did, where we pulled the red jack first and then the black card second. So let's switch up that order and just see what the impact is. So probability of black times probability of red jack. Okay, is it going to be higher or lower? We don't know. Let's see. So first of all, probability, we're replacing the card. So but first probability of black is 26 out of 52. Now we replace the card, so it's still 2 out of 52. And the thing is that this is one case, right? So we would get for this one, we would get 1 out of 26, right? But for the, no, we don't. Never mind. Oops, I know what I'm doing. Rewind. This is a cases situation. Remember, we're doing cases, right? So we have 2 cases, and we have to add them together. So it's either, Saturday evening, I'm doing this video. So first, we could have the case where we go red jack and then black, right? Or we have black and then red jack. Okay, it's an or situation, or. So we'll see what the impact is. So red jack and then black, we would have 2 out of 52 for the red jack times 26 out of 52 for the black card, right? Or we could have the opposite happen and it would still be a legitimate situation. We pull the black first and then we pull the red jack. Remember, we're replacing it so the numbers don't change on the bottom or the top. Here we would get 1 over 52 plus 1 over 52. We add those together and we get 1 out of 26. Okay, so it's cases, so it actually increases our probability. So that does change how you're doing things. Now let's see what happens with the other circumstance. Here, if we have RJ and then black, right? or we have black and then RJ, okay? Or black if RJ already happened, RJ if black already happened, okay? So for our first example, we know it's going to be 1 over 51, right? And for this one, and again, they're cases, we're going to have, for our black card, it's going to be 26 out of 52, and then it's times 2 out of 51, and that will reduce to 1 over 51 as well, and we'll get our answer of 2 out of 51. Okay, so this is cases because if we're switching order, we have to look at both possibilities in order to make sure it works. Okay. One last page of examples. Sorry about that last one. I got kind of confused at what I was asking. I should know. Okay, example 5. Working backwards to determine probability. The probability that the Oilers will win a championship is 2 out of 9. The probability that the Oilers and Eskimos will both win a championship is 8 out of 63. So those are the things we're dealing with. This is the Oilers, and this is the Oilers and the Eskimos. Now, working backwards to determine probability. So what is the probability then that the Eskimos will win a championship? Well, we know that the combined probability is equal to the separate probabilities times each other. Are these independent or dependent events? Well, these are definitely independent because it should not have any impact on each other. So the probability that the Oilers and the Eskimos win should equal the probability of the Oilers winning times the probability of the Eskimos winning. So once we map that out, we just fill this in. So we have 8 out of 63 for the probabilities of both of them winning is equal to the probability of the Oilers winning, 2 out of 9, times the probability of the Eskimos winning. We're going to rearrange and solve. So we do that by multiplying both sides by 9 over 2, right? Because that will divide out the 9 there and the 2 there. So 9 times 8 will get us, well, we can actually do some dividing, but 9 times 8 is, 9 times 8 equals 72 over 2 times 63 is 126, which is equal to our probability of the Eskimos winning. I can reduce that further down to 4 out of 7. So they're both divisible by 18. So if I divide 18 out of the top and the bottom, I get 4 out of 7. So you can work backwards with these relationships just to kind of make sure that you understand that they do connect. And they are a mathematical formula. It's just understanding what happens. Example 6. Determining the probability. There's a bag of 20 marbles. Let's see. 9 are purple. Okay. Gonna get fancy there. 3 are blue. 6 are white. And 2 are green. We choose 2 marbles without replacing the first one. Are these events independent or dependent? Does it matter if the first is replaced or not? It does matter. These are dependent. Whatever you pulled first is going to impact the second. So yes, it matters. It changes the number of marbles. Okay. So find the following probabilities if possible. So drawing 2 purple marbles. So the first one is going to be 9 out of 20, right? The second one, we pulled 1 purple marble, so we'd have 8 left, and we'll have now only 19 in total, right? So we multiply through 9 times 8 is 72 over 20 times 19 is 380. I can divide the top and the bottom by 4, and I'll get 18 out of 95 for that probability. Drawing no purple marbles. Well, 11 out of 20 are not purple, times, once I pull a marble out, but not a purple one, I still have 10 that are not purple out of 19. So that would be 110 out of 380, and that reduces to 11 out of 38. Drawing a purple marble, then a white marble. So we draw our purple marble, and then we draw our white marble. So we have 6 white marbles, but now we only have 19 in total, right? So this is probability of purple times probability of white if we pulled a purple, okay? We multiply this. 9 times 6 is 54 over 20 times 19, which we know already is 380. And I can divide the top and the bottom by 2, and I'll get 27 out of 190, okay? Drawing a purple marble and a white marble. So in this case, order's not important. So we figure purple white and then white purple. So purple white we've just done. So we know that it is 27 over 190, right? That's this one here. And then for white purple, we would pull 6 out of 20 times 9 out of 19, because we have 9 purple, but now we only have 19, which is equal to, if we multiply those through, 6 times 9, oops, I divided. I keep wanting to hit the division button. I get 54, 54 out of 380, which it reduces to 27 over 190, right? So I'm going to add them because it's an OR statement. So when I add them together, I'm going to get 27 over 190 plus 27 over 190, which is equal to 54 over 190, which reduces to 27 over 95. And that's just your fraction work. I think the big thing to understand is that when you, in this situation, it's sequence was important, and here sequence was not. So this means you have cases. Okay. Okay. All righty. Well, hopefully that makes sense for you guys. Time to practice. So we have independent events and dependent events. Independent events are events which the first outcome does not affect the outcome of the second. So if we replace cards, we're pulling from 2 different bags, or they're 2 things that don't impact each other, like dice and spinning, or 2 different dice, that sort of thing. We can use the product rule for independent events, and the probability that 2 independents will both occur is the product of their individual probabilities. Dependent events are 2 events which the outcome of the first does affect the outcome of the second. So this is if you do not replace. So you take a card but you don't replace one. And we have a slightly different formula because this second part here means that B if A has happened. Okay? So we write that a little differently, and it's going to affect our probability. We can use a tree diagram. Those are very handy to help us explain or map out our sample space in terms of what's happening. The word neither means the complement, right? It's the things that are not what we want. So neither means the complement of the first event and the complement of the second event. Sometimes replace